The photoelectric effect, as we've talked about for 3 days now, says when light strikes a piece of metal, an electron is sometimes ejected. And that electron is going to be ejected if the photon is of sufficient frequency and therefore sufficient energy to cause the electron to be ejected. If we up the frequency of that photon, then you will get a more energetic electron ejected. If you up it a lot, like I'm talking a lot to the range of maybe X-rays, which is a really, really high energy photon, then maybe you don't just get an electron ejected, maybe you now get a photon ejected as well, a second photon, not the original photon. This photon is different. This photon is less energetic than the first one. So if an X-ray struck this, caused an electron to be ejected, maybe you get the electron and a less energetic X-ray, or maybe even an ultraviolet photon that's ejected. Now, classical theory, which we say is kind of pre-20th century physics, all the way up to the year 1900 about, classical theory would have predicted that, look, if you're going to have a photon that's ejected here, it's not going to be any different than the original photon that you had. If a certain frequency of X-ray caused an electron to be ejected, then you got another photon out of it, then that photon that you got out of it would be the same photon. You can't just change a photon into another photon. You can't just change light into another color or another frequency, according to classical theory. But quantum theory, or photon theory, or the particle theory of light, says that you can. Compton explained this. A guy named Arthur Compton explained it using photon theory, Einstein's photon theory, as well as a couple ideas of his own. He said that, look, this interaction between the photon and the electron and the second less energetic photon is really just a collision. It's just a collision. And we've known for years and years and years how to deal with collisions. We learned it back in February. We do use the law of conservation of momentum to deal with collisions. But if we use the law of conservation of momentum to deal with this collision, it's making a pretty big inference. The inference is that not only electrons have momentum, but photons have momentum as well. That's a big deal here, and that's one of the big takeaways from this. Photons have momentum. They don't have any mass, but yet they have momentum. And that seems to contradict what we learned in Unit 1, right? We said in Unit 1, a momentum is equal to m times e. How can a photon have momentum when it doesn't have any mass? It's got velocity, but it doesn't have any mass. We'll deal with that in a minute. Bottom line is, photon theory, quantum theory, says that photons do have momentum. And they must have momentum because that's the only way that we can explain the observations that are made with the Compton effect, that an electron is ejected and a second less energetic photon is ejected. Now, just a couple of kind of little tidbits to kind of tie things together here. I wouldn't lose too much sleep over the difference in the terminology here. Okay, I'm pretty sure that's not going to be a huge issue for you on a test. But just for perspective, the scattering of the photon, so the photon that strikes it, the photon that comes off at an angle, the scattering of that photon is called Compton scattering. And the change in energy of the photon, we said it loses energy, right? The change in energy of the photon is called the Compton effect. If one of the main takeaways from this is that photons have momentum, then we better talk a little bit more about the momentum of the photon. We said that electrons, protons, baseballs, semi-trucks have momentum equal to m times v. But what's the momentum of a photon going to be if it doesn't have any mass? Once again, for the second time this year, not for the last time, but for the second time this year, enter Einstein. Einstein said that energy and mass are really two different forms of the same thing. They're equivalent to each other. It's kind of like ice and steam in a sense. We're not talking about states of matter like ice and steam are, but in the sense that they're the same two different forms of the same thing? Okay, it's analogous. We can change ice to steam. We can change steam to ice. They are chemically identical to each other. Ice and steam are exactly the same thing, just two different forms of the same thing. Einstein said that energy and mass are also two different forms of the same thing. Not two different states of matter, but still two different forms of the same thing. And we can change energy to mass and mass to energy. So it's like that law that you learned about in grade 9, the law of conservation of mass isn't true. We lied to you. That law that you learned about in Science 10 and in Physics 20, the law of conservation of energy, it's not true either. We lied to you. Because you can lose energy. You can destroy mass, kind of. You can change mass to energy, and you can change energy to mass. What we really should have called it in grade 9 and in grade 10 and grade 11, and earlier this year in grade 12, we really should have called it the law of conservation of energy / mass. Because it's not just energy that can be changed from one form to another. It's energy and mass that can be changed back and forth from one form to another. In the end, we still call it conservation of energy and conservation of mass because under normal circumstances, energy stays as energy and mass stays as mass. Just in certain situations, you can convert one to the other. So anyways, Einstein's energy-mass equivalence says that energy and mass, two different forms of the same thing, and we can relate their values together by using an equation. An equation that is probably one of the least understood physics equations ever, but probably one of the most famous, if not the most famous, physics equation ever. Anybody want to take a stab at what it is? Yep. E equals mc squared. If you have a certain amount of mass, you can multiply that by the speed of light squared and get a value for energy. It doesn't mean that it is energy. It just means it's equivalent to that much energy. If you have this much ice, it doesn't mean you have steam, but it's equivalent to this much steam. This equation tells us how much energy we would have if we converted mass to energy. And similarly, it tells us how much mass we would have if we converted energy to mass, the equivalent mass. So Einstein said, even if you don't have mass, as long as you have energy, you have an equivalent mass. So let's replace the mass in the momentum equation by the equivalent mass that Einstein came up with. So Compton says, look, the momentum of is not dependent upon the mass. It's dependent upon the equivalent mass, E over c squared times v. And then Compton said, well, wait a second. What's v? Speed, right? Speed of what? We're talking about the momentum of a photon. So Compton said this would be the speed of light. The equation would now become E over c squared times c. And c cancels. So we're left now with momentum is E over c. On your data sheet, in the very top right-hand corner, this actually appears in a slightly different form. E is equal to P times C. Compton said that photons have momentum. And that's how we explain this second less energetic photon that's ejected in addition to the electron. The momentum of the photon isn't related to the mass of the photon because there is no mass. But we can relate it to the energy of the photon. And that's good because we know the energy of the photon is HF, right? Or hc over lambda. That's easy. Now, Compton also derived another equation, said, look, E is equal to hc over lambda, right? So we can say E is equal to hc over lambda, or hc over lambda is equal to P times C, the momentum times the speed of light. C cancels. Now we're left with P is equal to h over lambda. Another equation that appears in the top right-hand corner of your data sheet. This one relates momentum of a photon to not energy, not mass, because there is no mass, but it relates it to the wavelength of the photon. This one, by the way, also appears in the top right-hand corner of your data sheet, but it's not unique to the Compton effect. It's not unique to photon momentum. Okay, we deal with that anytime we've got a situation where we're dealing with an energy-mass equivalence thing. Okay, not just in this situation. If you're looking at your data sheet right now, you're going to see there's actually one more equation up in the top right-hand corner as well. It's this one. Delta lambda is equal to h over mc times 1 minus cosine theta. This does not look pretty. The good news is it's not as bad as it seems. Delta lambda, what does that mean? Change in wavelength. If the energy of the photon decreased, right, the scattered photon has a lower energy than the initial photon, right? Remember, it produced an electron and a second less energetic photon. If the photon lost energy, then the wavelength of the photon's got to change as well. The color of the photon changes as well. If the energy goes down, then that means the wavelength will go up, because E is equal to hc over lambda. So energy goes down, delta lambda will be a positive value because it's going to increase. The final value will actually be bigger than the initial value. Now, we can solve for delta lambda using lambda f minus lambda I. That's actually not on our data sheet, but that's okay because anything delta is final minus initial, right? The second part of the equation is the part that's on our data sheet, and that's good because that's the one that's a lot harder to remember. Delta lambda is equal to h over mc times 1 over 1 minus cosine theta. Delta lambda is the change in wavelength of the photon. It's going to be a positive value. It's always going to be an increase in the value of the wavelength. And the units are going to be meters. H is Planck's constant. And the value we're going to use for this every single time is 6.63 times 10 to the minus 34. Don't try using the electron volts for this. M, it's a mass, right? Mass of what? What are we dealing with there? Mass of what? No, it's a good guess, but it's not the theoretical mass or the mass equivalence of the photon. We're dealing with something here that has mass. What is it? X-ray strikes a metal, an electron is ejected, a second less energetic photon is ejected. What has mass? The electron. This is the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And c is the speed of light, which is 3.00 times 10 to the 8 meters per second. Now, if it was me, I would replace these three numbers there, those three constants, with one constant, because those three are always going to be the same. Every time you do one of these questions, you're going to be doing this divided by this times this. Why don't we just have one number and replace all three of those with one number? I'm not sure. Not sure. But we don't. This is the way it appears on our data sheet, so this is the way we'll do it. 1 minus cosine theta. What's theta stand for? It's an angle, right? But what angle? It's a scattering angle. The angle that something scatters at. The scattering angle of the, fill in the blank. The electron or photon, it's the photon. The scattering angle of the photon. Here's the way we remember that. The electron's not really scattering, right? The electron was in the metal. It's the photon that hits it and then scatters at a new angle, right? So it's going to be the scattering angle of the photon, not the electron. Now the good news is there's not going to be much rearranging of this equation to do because in the end, H and M and C you've already got. Those are constants. The only thing you may have to rearrange to solve for is theta, which is a bit of a pain here if you have to rearrange to solve for theta, but it's not too bad. And in the end, you don't have to do that most often anyways. We've got a couple examples that I want to do with you today. The first one, unfortunately, doesn't appear in your book. So I'm going to ask you to copy this one down, please. Here. The question says, calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. That's lambda. We're going to circle the nanometers in red because we want to convert that. We know we're going to convert that to meters. We want to find the energy, and we want to find the momentum of that photon. Now, let's do the energy first because we've done that for almost a week now. least 4 days. The energy of a photon is simply equal to hc over lambda. That's not new. We didn't do that today. We did that last week. The energy of a photon is hf or hc over lambda. Let's put in a value for h. What do you want to use here? 6.63 or 4.14? 6.63. Could you use 4.14 here? Sure you could. Sure you could. This equation, you use whatever you want, whatever's convenient for you. Okay. If in doubt, use this value because you can always get away with the 6.63 value. We do the math there, and I think it worked out to be 3, if I remember, 3.315 times 10 to the negative 19. Anybody get that? Which we're going to actually round to 3.32 times 10 to the minus 19 joules. Now, you could have done that in electron volts, or you could take this and convert it to electron volts. That's the energy. Again, nothing new there. The momentum, however, is new. How do you find the momentum of that photon? We'll look in the top right-hand corner of your data sheet under quantum mechanics in nuclear physics. We get two equations that relate the momentum of a photon to some other property of the photon. E is equal to P times C. P is equal to H over lambda. Which one do you want to use? Abby? Mason? That's right. Okay. I was going to say the other one, but that's okay. That's okay. E is equal to P times C. Does that work? Sure. Why does it work? Because you just solve for energy. Well, we know the energy is 3.315 times 10 to the minus 19. Got that. Got the speed of light. Solve for the momentum. Okay, now the way I was going to do it, Mason, but my way is not better than your way here, is going to be the other equation, H over lambda. Got the value of H, got the value of lambda. Solve for the value of P. Now, I'm going to use this equation here, Mason, not because it's better, but just to demonstrate one thing to you. When you're using any of these Compton effect, photon momentum, photon wavelength equations, let's use the value 6.63. Energy, doesn't matter. But momentum, use the value 6.63 times 10 to the minus 34. But it's getting even more confusing, right? When to use 6.63 and 4.14? Is it confusing you a little bit? If it's confusing you at all, what should you do? Just use 6.63. (1.11 times 10 to the negative 27. And the units for this seems a little bit odd to talk about kilograms for a photon that doesn't have any momentum, but those are the standard units for momentum, kilograms, meters per second. I'm going to give you a couple of minutes, and literally just a couple of minutes to work on the practice problems that go with this. And then I want to do one more example before the end of class here, okay? So flip the page here, work on these questions right now for a couple minutes, and then we'll spend some time going over one more example. One little thing that I want to caution you on right now before you work on these is number 3. You want to find the energy gained by the electron. Well, it's going to be equal to the energy that's lost by the photon, right? The change in energy is going to be the final energy minus the initial energy. It's going to be hc over lambda f minus hc over lambda I. Do not do this. This is what some people are going to want to do. Don't do this. The only time you can arbitrarily stick a delta into something is if it's on the top and it's not squared or anything, if it's a linear relationship. Okay? E and lambda aren't linear. You can't just stick a delta in there and make that work. Let's take a look at one more example here on page 724, and we'll wrap it up here after we're finished this question. It says an X-ray photon with a wavelength of 0.0500 nanometers. Circle the nanometers because we don't want to stick with that. Scatters at an angle of 30 degrees. What do we got here? X-ray with a X-ray photon with a wavelength of 0.05 nanometers. That's a wavelength, right? We got to be more specific here, though. Wavelength what? If we read on in the question, it says calculate the wavelength of the scattered photon. Don't we already have the wavelength? No, there's two wavelengths, this wavelength and this wavelength. What's the one we have, Colin? This is the initial wavelength. We're looking for the final wavelength there, the scattered photon, the final wavelength. What would you predict that it's going to be, bigger or smaller? The energy of the photon goes down. The wavelength of the photon goes up. So you don't get a bigger number for this. You made a mistake, right? You know it's going to be a bigger number. Okay, this is going to be theta, of course, the scattering angle of the photon. Let's use that ugly looking equation that we learned a few minutes ago. Delta lambda is equal to h over mc times 1 minus cosine theta. And let's find the value of delta lambda. Once again, we're always going to use the value of Planck's constant 6.63 for all of these Compton effect equations, all of them, no exceptions. The mass of the electron is 9.11 times 10 to the minus 31, and the speed of light is 3 times 10 to the 8. Now, it looks ugly, but we'll do this on our calculator. We'll find that it's actually not that bad. Let's see, 6.63 times 10 to the minus 34, divided by, use some brackets down here, 9.11 times 10 to the minus 31, times 3 times 10 to the 8. Get a number for that. Don't try to multiply everything else by it right now. Just get a number for it. 2.42 times 10 to the minus 12. Now let's multiply that number by bracket 1 minus cosine 30 degrees, end the bracket for the angle, end the bracket for the 1 minus cosine of the angle. 3.2501 times 10 to the minus 13 meters. Is that my answer? What have I just found there? Cool. Good. I found a change in wavelength. I want the final. So I'm going to say delta lambda is equal to lambda f minus lambda I, or lambda f is equal to delta lambda plus lambda I. 3.2501 times 10 to the minus 13 plus the initial wavelength, which is 0.0500 times 10 to the minus 9, equals, let's do that on our calculator now. Get 5.03 times 10 to the minus 11. We're dealing with a small wavelength, smaller than we're used to dealing with, right? Usually it's 10 to the minus 7. This isn't visible light. Okay, this is something higher than visible light. It's going to have a lower wavelength than visible light. All right, your questions for homework are the one question on page 724 and the 3 questions that you were working on a few minutes ago on 723 if you haven't already finished those.